Final exam review problems here in the packet, starting with number 1. What I'm really looking for you to recognize here is that we can't have, so no negative under an even index. Right, this would involve imaginary numbers, which we have not talked about since Unit 3 back in first semester, so we would just simply say at this point, does not exist. However, I go directly to number 2 here, where you've got a negative underneath an odd index. That's the key here. So because this is an odd index, we can have a negative underneath there. If you go to your powers chart and take the cube root of 343, it would be 7. So then the cube root of negative 343 would be negative 7, right? And you can always test it. Negative 7 times negative 7 times negative 7 is equal to negative 343. So there's our check mark on this. Okay, next one. If we are raised to a negative exponent, remember that flips us over the fraction bar. So the first thing I would do here is flip this over the fraction bar and say this is the same thing as 1 over 216 to the positive 2/3 power. One of the things I expect you to be able to do on this final is utilize a fractional exponent. So this is the same thing as saying 1 over the cube root of 216 squared. Remember, you really could put that squared exponent on the inside of the radical or out, but I don't know what 216 squared is off the top of my head, so I'm going to keep it out. Again, the cube root of 216 is 6. So this becomes 1 over 6 squared, which is equal to 1 over 36. Okay, our next one here in number 4, I would look at this and I'd say, all right, first things first, anything to the 0 power is 1, so just get rid of it. Next thing, I would apply the exponent on the bottom throughout that parenthesis. Remember, a power to a power, so what that really means is you've got x squared cubed, so power to a power, we multiply those exponents. So that's what we're going to do in the denominator in order to apply. So that would look like x to the 6th, y to the 12th. In the numerator, I still have x to the 9th, y times x to the 7th. Now, since I've got 2 bases up in the numerator with x's, I'm going to add those exponents. So I have x to the 16th times y in the numerator. I have x to the 6th, y to the 12th in the denominator. And then if we do a little canceling with x's versus y's, where are all the leftovers going to be? So I've got 16 x's on top, 6 on the bottom. So 6 of them are going to cancel out, and we'll be left with x to the 10th, 10 leftovers on the top. Same idea on the y's, except for all the leftovers, and there will be 11, right? Because this is like y to the 1st up on the top. This would be y to the 11th then in the denominator. Okay, next one here. This one's a little bit complicated, so I would just think about one step at a time, not trying to do too much in number 5. So I would look at this and say, I'm going to apply, similar to what we did in that number 4, I'm going to apply this 1/2 power. Remember, raising to the 1/2 power, let me just switch for a second. Raising to the 1/2, right? Anything to the 1/2 power is the same thing as taking the square root of it. So when I think of 4 to the 1/2 power, I'm really getting the square root of 4 in the denominator there. So if we just kind of leave the numerator alone for right now, 4 to the 1/2 power on the bottom would be 2. Again, power raised to a power for x to the 8th to the 1/2, so I'm going to multiply those exponents to get x to the 4th, y to the negative 3. And then we can go through and say, all right, anything with a negative exponent, not a negative number, so negative 10 is not going to go anywhere, but anything with a negative exponent is going to move across the fraction bar in order to become a positive exponent. So then this would look like, to finish this one up, we'd have negative 10, the y is still up there, and now we're also bringing up a y to the positive 3 when that crosses over. The 2 is still in the denominator, the x to the 4th is still in the denominator, and now we're going to have an x to the positive 2 when that x to the negative 2 moves down. So combining everything, reducing our fraction out front, this would look like a negative 5 with 4 y's on the top, right? This is like a y to the 1, so we add exponents, and then over x to the 6th in the denominator. For this number 6 here, again, looks like a doozy. Just start one step at a time. That's how these things get done. So this whole thing in parentheses is raised to a negative power. So just like we did up above here, we're going to flip things over that fraction bar. So I'm going to leave this first part alone, just so that I'm not doing too much in one step, and move this entire thing in the parentheses down. So 16x to the 8th, y to the negative 2, all raised now to the positive 1/2 power. And then this kind of resembles, in a very similar fashion, what we just practiced next door in number 5. So again, raising to the 1/2 power, I'm going to apply this exponent to everything. It's really like taking the square root. So the numerator, I'm going to just leave alone for a moment. This is 16 to the 1/2, which is 4, right? Because the square root of 16 is 4. X to the 8th to the 1/2. We're going to multiply those exponents, so x to the 4th, and then y to the negative 1. And again, very similarly here, anything that still has a negative exponent, so here and here, are going to cross the fraction bar to become positive. So this would look like negative 12y cubed, just staying up there, and an additional y to the 1 once it moves over from the bottom, all over a 4x to the 4th x squared. Again, very similar to number 5, reduce the fraction out front, combine your y's together, combine your x's together, so we get negative 3y to the 4th over x to the 6th. Okay, let's move on. 7, 8, 9, and 10 is all dealing with properties of radicals. So simplifying a radical that has both variables and numbers in there, we're looking at a 4th root. So we're going to, on our powers chart, we would look at that n to the 4th column, and we'd say to ourselves, is there a perfect 4th that goes into 162? And the answer is yes. 81 times 2. 81 is a perfect 4th. In order for a variable, like a, b, and c up here, in order for a variable to be a perfect 4th, it has to be, the exponent has to be divisible by that index. So 28 is divisible by 4, so 7 times. So a to the 28th, that is a perfect 4th, so that's going to come on out. B to the 9th, the 9 does not divide the 4 evenly, but we could break it up as b to the 8th times b, and then this guy can come out. That's a perfect 4th. And c cubed is the actual exponent here is less than the index. 3 is less than 4, so that's not going to come out. So everything that's circled right now is a perfect 4th and is going to come out to the front once we take the 4th root. So the 4th root of 81 is 3 when it comes out front. The 4th root of a to the 28th is a to the 7th. The 4th root of b to the 8th is b squared. Because b squared times b squared times b squared times b squared, there's our b to the 8th, right? We're asking ourselves to times itself 4 times. And then what's left inside the 4th root is the 2, b, and c cubed. It's all the things that we didn't circle. In number 8, we're really just looking to practice our FOILing skills with radicals, making sure that we recognize that this is a FOIL situation. So if we set this up, 3 square roots of m plus 4 square roots of 2 times itself. So again, 3 square roots of m plus 4 square roots of 2. For our first terms, 3 times 3 on the outside is 9. Square root of m times square root of n is just m. For our outside terms, that would be 3 times 4 on the outside is a 12. Square roots of m and 2 are both inside the radical, so square roots of 2m. And then again, similarly on the inside, very similar situation, we have another plus 12 square roots of 2m. And then finally, our last terms, this guy and this guy. 4 times 4 is 16, so plus 16. And then the square root of 2 times square root of 2 is 2 with no more radical. So this actually becomes a 32, no more radical for that last term. We can also combine our like radicals in the middle to have 24 square roots of 2m. And then we've got this 9m out front, and nothing anymore are like terms, so we would simply circle this and be done. In number 9, we're looking for simplifying radicals so that we might be able to get some like radicals. So I look at square root of 75 and I think, Well, 25 times 3, the 25 is a perfect square. Minus 2 times the square root of 27 is 9 times 3, and then 9 is a perfect square. And then plus 8 square roots of 3, that one does not simplify anymore. So I'm looking at this kind of similar to how we did the fourth root over here. If it's circled, we can take it out of the radical. So the square root of 25 is 5 square roots of 3 minus, when we take out the 9, that becomes a 3, and everything is connected by multiplication. So this is going to be really 2 times 3, and then the square root of 3 is still left there. So this really becomes minus 6 square roots of 3 in the middle. And then we've got this plus 8 square roots of 3 tagging along. So this is kind of, it's not the same problem, but I want you to think about it like 5x minus 6x plus 8x, right? How many x's do you have? Right, so if we were to combine these, we'd end up with 5 minus 6 is negative 1x, plus 8x is 7x. So very similar for our situation, how many square roots of 3 do we actually have? 5 square roots of 3 minus 6 square roots of 3, this is negative 1 square roots of 3, plus 8 more square roots of 3, we end up with 7 square roots of 3. Okay, so combining over here, we've got a cube root, so I'm trying to show you lots of different things to practice here. The first thing, not to simplify each individual root, but combine into one big root, and then do what we practiced over here in number 7, but with a cube root versus a fourth root. So let's combine everything. Notice right here, if you've got 5uv squared, that's really going to be 25u squared v squared underneath that radical. Right, so you've got the cube root there of 25u squared v squared in place of this, just so that it's simplified. And now we can combine the cube root of this 10u squared v out front times this one. We actually just combine the pieces together. As long as they have the same index, we can put them into one big radical. So 10 times 25 is 250. U squared times u squared is u to the 4th. V times v squared is v cubed. And so now we're going to look at this like we did in number 7, and I'd say, well, 250 is not a perfect cube, but 125 times 2, the 125 is a perfect cube. U to the 4th, 4 is not divisible by the index of 3, but we could write this as u cubed times u, and then the v cubed is divisible by that index 3, so these are also perfect cubes here. So when we take the cube root of 125, we get 5. The cube root of u cubed is just u, then v, and then we're left with the cube root of 2u. Okay, number 11, this is a big page. 11, 12, and 13. We're trying to rationalize the denominator, which is getting rid of radicals in the denominator. So I multiply, square roots are generally the easiest. We just get in the habit of kind of multiplying top and bottom by that square root. So this ends up looking like 15 square roots of 6x. Remember, we can't combine numbers out of a radical with numbers in, so we have to leave them as is. Square root of 6x times square root of 6x is just 6x. So I've had a couple of questions about this. Remember, at this point, you still want to look and say, can anything simplify? And since both the 15 and the 6 are outside of the radical, we can reduce this to everything's divisible by 3. So 5 square roots of 6x all over 2x. For the next one, I would do some simplifying first and see if you can get some canceling so that it's easier to rationalize. So let's do this. This would look like the cube root of, well, 8 over 48. We'd be left with 1x on top. 8 over 48, we'd be left with a 6 on the bottom. It's like 1/6. And then with a y squared. Nothing's going to simplify with that y squared. So we're really trying to rationalize here. If we break this apart into two separate radicals, the cube root of x, and then the cube root of 6y squared. So we've got to make a perfect cube in the denominator. So simply just multiplying the cube root of 6 times the cube root of 6, we would end up with the cube root of 36, which is not a perfect cube. So we're going to try to get to 216, which means I've got to multiply the bottom by the cube root of 36. I've got 2 y's underneath the cube root. I need another y to get 3 of them, which is a perfect cube. And whatever we multiply the bottom by, we have to multiply the top by. So this would be the cube root of 36y on the top as well. On the top then, this becomes the cube root of 36xy all over the cube root of 216y cubed. And by design, both of these things in the denominator, you could probably skip this step. That's a perfect cube and that's a perfect cube because that's what we've set up here, is to make sure that that happens. So the cube root of 216 is 6, the cube root of y cubed is y, and then up top we've got this cube root of 36xy. Over here we're going to have to use the conjugate. So that's probably a word we haven't talked about for a while. So if we have the square root of 2 minus the square root of 3, then the conjugate would be the square root of 2 plus the square root of 3, right? It's like the same binomial, but the sign is changed. So what we're going to do then is we're going to multiply top and bottom by that conjugate of the denominator. So this is going to require a little bit of work. I always check the denominator first, so I'm going to do that again here. So foiling, right, down here, square root of 2 times square root of 2 is 2. Outside terms, square root of 2 times square root of 3 is a positive square root of 6. Inside terms will give us a negative square root of 6, so that's the design here. We wanted that to happen. And then finally, our last terms, negative square root of 3 times positive square root of 3 is a minus 3. So these guys are going to drop out in the middle, and we're going to end up with a denominator of 2 minus 3, which is negative 1. So this looks good. Let's finish by foiling the top as well. So 1 times the square root of 2, right? So now we're just foiling the numerator, kind of coming back here. So first terms, 1 times square root of 2 is just square root of 2. Outside terms, 1 times the square root of 3 is square root of 3. Inside terms is 3 times square root of 2 times square root of 2, which is 3 times 2, which is 6. And then last terms would be 3 square roots of 6. So all of these are different radicals in the numerator, so nothing can combine. So we could just simply bring them down. Square root of 2 plus the square root of 3 plus 6 plus 3 square roots of 6 all over negative 1. This is not what you're going to see if you were to check the answer at the back, because if you're dividing by negative 1, it really just switches all the signs for everything up above. So this is really going to be negative square root of 2, negative square root of 3, negative 6, and negative 3 square roots of 6. Why have a fraction if we don't need one? Okay, number 14, 15, and 16. Let's move on to those equations down at the bottom. So the goal is always to get the radical by itself. So our first move is to subtract the 10. So we end up with the square root of 12x plus 12 equals 2x minus 10. Once you've got the radical alone, we undo a square root by squaring both sides. That means foiling over here. So this goes away on the left. We end up with 12x plus 12 equals, right? The math that we're really doing here is 2x minus 10 and 2x minus 10. Foil that out, so we end up with 4x squared. Minus 20x minus another 20x is actually going to be a minus 40x plus 100. This is definitely going to be a factoring scenario, so let's go ahead and get everything equal to 0. Subtracting this over, minus 12x minus 12. We end up with 0 equals 4x squared minus 52x, and then a plus 88. So this kind of looks scary as far as numbers go until we recognize that everything is divisible by 4. So let's make our life easier and get rid of that. So we get 0 equals x squared minus 13x plus 22. What are the two numbers that multiply to 22 and add to negative 13? I think you'd say negative 11, negative 2. And because we divided off the 4, there's really a 1 out front here, which means we can just put the numbers right into the binomials. So this becomes x minus 11, x minus 2. When we go ahead and use zero product property, either the x minus 11 equals 0 or the x minus 2 equals 0, which means x equals 11 when we add it over, or x equals 2. But remember, we have to check for extraneous solutions. So the first thing I would do is go back up here and say, does this work? So 12 times 2 is 24, plus 12 is the square root of 36, plus 10 equals 2 times 2. So 6 plus 10 does not equal 4. So this guy cannot possibly be a solution. When we go up and check, I'll do this in a different color just so that we can see it clearly. When we go up and check the x equals 11, we get 12 times 11 plus 12, 132, plus the 12, we end up with the square root of 144, plus 10 equals 2 times 11. Square root of 144 is 12, plus 10 is 22, equals 22. That guy checks out. So this is the only solution. This one right here is extraneous. In number 15, right next door, the first thing we want to do is divide off the 2, right, to try to get that x or that radical. Technically, a fractional exponent is a radical. So to get that alone, so we end up with 25 is equal to x to the 2/3. So you could leave it this way, or you could recognize that you're really solving the same equation by solving 25 equals the cube root of x squared, right? These are solving the exact same equation. I'm going to leave it on the left, but you are welcome to undo the right one by saying, hey, I can undo a cube root by cubing it, and all of those things. I'm simply going to say, go back to what we talked about in Unit 6 and say, hey, how do we undo a 2/3 power? By raising both sides to the reciprocal 3/2 power. Right, so over here, power to a power, we multiply, those go away, we end up with x is equal to, but it's our job on the left-hand side to recognize that this is really the square root of 25 cubed. And so because that's an even index, we need a plus or minus, So I'm going to go ahead and add that in right here. That's kind of the tricky part that we've got to remember. So this is really plus or minus square root of 25 is 5 cubed is equal to x. So this is plus or minus 125 is equal to x. And then over here in number 16, we actually have 2 radicals. And in these scenarios, we said isolate the ugliest radical. I would say the ugliest radical is this guy. It's always the bigger radical, and it's already alone. So let's go jump right in and say, let's square both sides. Remember, this means foiling on the right-hand side. We cannot just foil or square the individual pieces. So over here, squaring a square root, we're just left with 3x minus 5 equals. Over here, we're going to set ourselves up to FOIL. Square root of 3x minus 1 times square root of 3x minus 1. So this is equal to square root of 3x and square root of 3x is 3x minus 1 square root of 3x minus another 1 square root of 3x when we do the outside and inside terms. So that's minus 2 square roots of 3x and then plus 1. And on the left-hand side, we still have this 3x minus 5. Combining like terms and trying to now get our remaining radical all by itself. The good news is when we go to subtract off this 3x, that's wonderful. So we've got then subtracting off the 1, subtracting off the 1, so we've got a negative 6 equals negative 2 square roots of 3x. Please be very careful and note that we can't just add the 2 over because it is connected by multiplication. So we would have to divide off the negative 2. This leaves us with a positive 3 is equal to the square root of 3x. We undo that last square root by squaring both sides. So we end up with 9 is equal to 3x. Right? Square and square root undo each other. And then finally, to get x alone, we divide off by 3. So x is equal to 3. We would still want to check for any extraneous solutions. So if you put this back up, a really quick check here. 3 times 3 is 9 minus 5, square root of 4. So that's okay. Equals Square root of 3 times 3 is square root of 9, which is 3, minus 1, which is going to be 2 on this side. So this guy checks out. Square root of 4 is equal to 2.